All right, let's get started. I'm going to turn off my video. And all right, cool. So as you guys know, homework 3 is due today at 11:59 p.m. You lose 10% you lose 10 points every day that it's late. You can submit it late, but you will lose points. Regardless, I encourage you to submit it. Even if this week was a bad week for you, so you didn't have time to do it. Again, if you are trying your best and you're trying to learn, then like reach out to me and I can work, like we can figure something out. If you just completely disappear, then I can't really help you, right? So if you submit nothing and then you come to me at the end of the semester and you're like, that's pretty bad, then I can't really help you at that point, right? Cool. Next up, homework 4 is going to come out today at 5 p.m. So you guys don't really get a break in between homeworks anymore, but that'll be out for all of you that already finished the homework. So you can go ahead and get started on next week's homework. It is going to cover basically the last 3 lectures, including this one. It's going to have some questions about that as well. It's going to be written and coding. So very similar to what we've done before. Yeah. Yeah. Yeah, so disappointingly, I did not get time to add Python to homework 4. So this one will still be in C++, but I am trying to figure out how to make time. I guess adding the 10-minute conversations with each of you actually took a lot more time than I wanted. But I think that's more valuable. I am trying to get Python included as an option for the homeworks at some point. For this one, sadly, it is still in C++, but again, I think more than half of the class was sort of okay with that. For the rest of you that prefer Python, I also prefer Python, so I will try to make that an option. But I essentially need to write like a new auto grader and then actually make the homework for both of them. Cool. What I can try to do for homework 4, I might be able to get a Python version out, but it might be like a little bit later than what I released today. So I might try to do that, or I might just call it quits and do it for homework 5. Okay. But I am trying. So thank you for reminding me, and I haven't forgotten. I do want to do that. Yeah. All right, so let's get started with lecture. So here's the link. We wrote up some code. So again, like I mentioned, in industry, a lot of your work is actually reading other people's code and understanding what it's doing. So from the lecture slides, I actually linked out to a replit that you guys are more than welcome to jump on if you would like to. And this replit actually implements counting sort and radix sort. So the 2 sorting algorithms that we were talking about last time implements them in C++. So what we're going to do for the first 7 minutes is we are going to walk through this code, and I want you guys to help me understand what the code is doing. Right. So again, we learned the algorithms last lecture, so you should have an idea of what the code is supposed to do. But now we're looking at the actual code. So for example, who wants to get me started on what this function is doing? Yeah. Yeah, that's great. So the very first thing when you're looking at code, look at the name of the function, and then look at the input and the output and the input, right? So that helps a lot. So we're looking at vector of pairs. What I would normally do at this point is kind of get a sense of what a pair is, because I'm like, what is that? Is that an int? Is that something? So in Replit, you can actually just go to definition. So you might say, well, what's a pair? And this is a pair. Somebody want to explain to me what that syntax is? And yeah, Leander in the back. Got it. Great. So actually, in this case, we created a structure. So this is not our normal, it's not normal integer, it's a structure with 2 elements. It has a key and a value. They both happen to be integers. Now, it will become clear to you why we did this, but you can implement counting sort in a different way. But the way we're going to implement counting sort is we are not going to sort the values. We are going to sort using their corresponding key. And you can imagine this is helpful because when we do radix sort, we say sort this array by the middle digit, right? So this helps us because we can say, well, let's put the key as the middle digit, sort by that, and then I get the values, all right? So that kind of helps answer that question. So now you have in your mind what a pair looks like. and you jump back to the code. So who wants to walk me through the rest of what this is doing? Somebody else? Vincent, yeah. All right, yeah, so he's getting the first two lines. It creates a vector of vectors of pairs that we call the buckets, right? So everybody gets like, so it's not just a single vector, it's creating a bunch of buckets, and each bucket actually holds another vector. So there's many ways to do this. You could use a linked list here. You could use a normal array. You could use many different data structures, but here we use the vector of vectors, okay? Hopefully this makes sense to you guys, but it's just getting the maximum key in our vector, and it's creating that many buckets plus one. Okay, so this max index, again, this is actually a function I wrote. So you might, what I normally do when I read that code is, if I don't really care about the details, I just pretend that what the function says it does is what it does. So here I would actually just be like, all right, yeah, that returns the max index of values. Seems fair. It's probably getting the maximum value, right? You might want, if you were debugging and you were running into issues, you might go up here and maybe read that code and be like, all right, maybe there's something wrong there, but there's not. But all it does is it iterates through and it returns the index of the maximum, the index of the pair in the vector with the maximum key, right? Because again, we're sorting by the keys, not the values themselves. The values are kind of just being brought along, okay? Cool. So who wants to explain the rest of it? What are we doing here? Yep, go for it. All right. Okay, and then yeah, keep going. Okay, yeah, does that sort of make sense to folks? So this for loop is just going over my input values, and it's saying, let me grab the key, and I'm going to put you into your corresponding bucket, right? Because we made this giant array that was from like 0 to 9, let's say. So this is grabbing the 0 to 9 index, and it's saying, I want to put you in that position in that vector. And that thing here is a vector itself. So we just say push back the value. So in case we have multiple values that go into the same bucket, right? That's why we did a vector of vectors, because we might have multiple values that end up in the same bucket. We just push them back. So that was the first step in counting sort. And then what we do is we iterate over all of our buckets. So we start with bucket 0 all the way up to bucket M, right? Because we could have up like the M value is the maximum value. So we iterate over all the possible buckets. If there's something in my bucket, then I iterate over that vector in the bucket and I add the value into my output, right? And then I return it. So this is the concatenating the, like once we've sorted them by buckets, we iterate over each bucket and we take the values in order as we see them. All right, so that's counting sort. Okay, any questions? Does that make sense? That should be like, we learned it last lecture, like in algorithm, and this is what a possible implementation might look like. You might not use vector of vectors. You could use a vector of linked lists. You could use a hash table. You could use a lot of stuff. Okay, so if we go to main, what I do is I have this vector 5, 4, 3, 2, 1, 2, 3, whatever. I print it first, and then I print the counting sorted version of it. So I sort it using counting sort, and I print that. So if we run it, you should not necessarily be convinced that this code is 100% right, but at least in one example, it does seem to sort the vector. Okay, cool. So let's jump back a couple more minutes. So that's counting sort. Who wants to walk me through radix sort? So again, you will notice that these sorts are not super crazy complicated. I would say it's maybe looks like 9 or 8 lines of code. So, yeah, who wants to walk me through this one? Jonathan? Anyone want to walk me through the code? You already know what it does. So it's now you're just looking at the code and being like, well, the first thing it should do is something. We also talked about, so I'll start you guys off. So the very first thing I do is I calculate a reasonable base. So we did talk about how radix sort, the running time depends on the base you choose for your digits. So what we did is we showed in lecture that if you pick the base to be the size of your input, that gives you a pretty reasonable running time as long as the values inside your vector are not super large. They're not exponentially larger than the size of the vector, right? So the very first thing we do is we get the base and we set it equal to the values that size. So essentially we set it equal to n, right? Then this part, you guys already know from counting sort, we just find what is the biggest value in our vector, right? Who wants to walk me through the last, it's a for loop. It's a little bit, yeah, Leander in the back. Yeah, yeah, okay. Yeah, so I think that's basically right. So basically what we do is we create our output vector that is a copy of our input vector, okay? So it's not sorted, it's just a copy of the input. Then what we do is for each digit that we computed, here we computed how many digits we had, which if you guys remember is the ceiling of the log of the maximum value base to the log of m base our base, which by the change of base formula, you can calculate this way. So this is log base 10, I think, in C++. But by the change of base, you just divide by log of the base you want. We take the ceiling and we add 1. So that gives us how many digits we have in the biggest number. So if we're doing base 10 and the number is 1,000,000, then we have 7 digits. So this will give us 7, right? And then for each digit, from 1 up to d less than or equal to digits. So that's exactly 1, 2 digits, right? We first update the keys. So you don't know what this does yet. And then we call counting sort on the output, right? So one thing you want to know is what does update keys do? This is what it does. So there is a comment there, but who wants to explain to me what it's doing? Yeah. 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 So basically remember we have these pairs and we're saying that counting sort sorts by the key, not the value. So what we're trying to do here is we're trying to set the key equal to the single digit that we're trying to sort by, okay? I'm actually realizing there might be a bug in this code that does not show up. So I will fix it after lecture. If you guys know what the bug is, feel free to fix it. I think you should be able to edit the replit. There is a bug here in this implementation as a challenge to you guys. It's not an obvious bug because the code is not wrong, but the code is not doing what you expect it to do. Like there's a bug more in the algorithm itself. And I would say if you want to find it, you would focus essentially what's going on. Like I think this logic is a little off. Okay, so that's one thing. Not in like the steps make sense, but if you think about it, we like update the keys to be the digit. We sort by the keys. And then on the next iteration of the for loop, I think there might be a bug, maybe not. I don't know. I'll let you guys think about it. But does everybody understand? So this is an implementation of radix sort. Is that a little bit clearer to you guys now that we covered the algorithm and then looked at it? I will leave the link on, the link is on the course website and on the lecture slides. So if you want to take a look at this code afterwards, I do encourage you to kind of read it. The expectation is that you should 100% be able to read this code and understand what it does. if you can reproduce this code on your own without having to look stuff up, that's awesome. That's really great. Okay, cool.
Question.
Yeah.
Could you go over why, let's say we have a bucket of size 100
Yeah.
items. Could you go over why changing the base to a certain base, let's say 99, reduces our bucket size from having to need 99 buckets to only needing like very few? Could you go over
Yeah.
concepts?
Yeah, we can look. So it's on the previous lecture. I will give you so it is not that it like, so the number of buckets we have is now equal to like the size of our vector, right? So if our vector is very large, we will still make a lot of buckets. But the thing we are avoiding is the case where in counting sort, normally you could have a vector that is like 2 elements. And then because one of them is, 5,000, you make 5,000 buckets. But it is still true that radix sort will still use, but like, again, like it won't use more memory than like you should, if you're being given an input of size, let's say 1 gigabyte, and you can accept that, then you only create, whatever million buckets that size of the input is. So your algorithm should be able to have that much extra space. So the amount of extra space we use is essentially the same, like it's O of n of the size of the input. So that's one of the benefits of radix sort. And yeah, let me see. I would encourage you to look at the lecture slides from last one. We did at the very end, we covered a little bit as to why we want it. Like it's essentially has to do with the running time being like d times n plus r. And then we said, oh, if we choose r, which is our base, to be equal to n, then it kind of disappears in the big O, because then it's just d times n. And then d is like log base n of m. And we said, okay, log base m of n is a constant if n is like not, if m, which is the biggest number in the array, is like n to the c. So it's polynomial bigger, right? So it could be big, but polynomial. Otherwise, if it's like exponential, then taking the log base n of m will still be like a function of n. So then your running time is still not linear. It's like worse than linear. Maybe I just write that. So basically we were saying that like the running time of radix sort is like big O of d times n plus r, because this is the running time of counting sort. And then for each digit, we do counting sort, right? So what we said is like, well, if we take, like we want to get rid of r, so we take r equal to n, then this becomes big O of 2dn. And in big O, the 2 doesn't matter. So we like erase that. And then the number of digits, this is given by the log to the base, so in this case n, of the biggest number that we have, m, plus 1, right? So it's off by 1 or something. And then what we said here is we said, well, if m, let's say m was n to the c, where c is a constant. So the biggest number is like, the size of the vector to some power. So it's saying it's like growing polynomially. Then when you plug this m into here, if you plug n to the c, the log base n and n cancel, and you just get a constant c, which means when you plug it into the big O, it'll be like O of c times n. And this c is a constant, so it drops. So it's linear. But if this m is exponential, like if it's 2 to the n, then it doesn't cancel. It gives you like a function of n. So then the running time becomes a little closer to like, I think it's n squared over log n or something, but yeah. But that is a good question. I think the takeaway is that in practice, you choose the base to be the size of your vector. And then most of the time, that's pretty good. Like it'll give you linear running time, essentially. But if you expect to have really large values and very small vectors, you shouldn't use radix sort. Okay, cool. All right, so that's actually fine because today's lecture is going to be more of a review, I hope, for you guys. So we're going to cover a few data structures that you should have already learned. We are not going to go too much into the details, but we are going to be using them in future algorithms. So that's why I'm going to take this week to cover essentially balanced binary trees, and we're going to cover hash tables hopefully on Friday. All right, so here's a motivation for binary search trees. So essentially for data structures, usually there's 3 operations you're interested in doing. You're interested in searching for values, deleting values from the data structure, and then inserting new values into the data structure. Okay, so those are like the three common operations that almost every data structure implements in some way. And you should be very familiar with sorted arrays. Like you should know exactly what that is. And you should hopefully be very familiar with linked lists from your previous data structure classes. So the running time for each of these operations on these data structures is listed here. And one of the reasons why we go and implement binary search trees is that when you have a balanced binary search tree, you can have all of these operations in log n time. Okay. Whereas here in search for sorted arrays, searching takes log n because you can use binary search, but deleting and inserting elements takes O of n because you have to move the element. Like if you delete one, you can't, like you have to move all the ones after back one. And there's just no faster way to do that. That's just like the way arrays are defined as a data structure. That is what you have to do. When you insert an element, you have to make space for it if it's somewhere in the middle. So you have to like move elements as well. And it could be all of them. Like if you want to insert at the beginning, that means you have to make a copy of the array where like, and then the first element is like whatever, right? Linked list, you can delete in O of n time because you have to find the element and then delete it. But you can insert really quickly because you can just insert it at the head. You don't have to do any work. But again, searching, because the list is not sorted, is you just have to go through the whole list until you find the number, right? But for balanced binary search trees, all of these you can do in log n, which is pretty good. And then tomorrow is like on Friday, we're going to talk about hash tables where you can actually do all of these in expected constant time. Okay, so hash tables use some randomness, but you can get expected constant time. Cool. So a quick review, binary tree. This is what we call a node, okay, in a tree. It has the key 7. For today, we're going to assume that all keys are distinct. As you guys have noticed, for a lot of algorithms, we assume things are distinct. It just makes we don't have to worry about some of the details. But when you actually implement the algorithms, you should probably ask yourself, are my keys always distinct? We call the very top node the root, okay? And we call the very bottom nodes the leaves, all right? This is just terminology. In a binary search tree, each node has 2 children. You can generalize binary search trees. They're called k-ary search trees with like a k and then ary, which basically means they have k children instead of 2. So binary is because they have 2, right? You can imagine trinary search trees have 3 children each. It turns out the running time doesn't change with k. It's all log-based k, and like all logs are the same in Big O. Cool. The left child of 3 is 2. So you have something called a left child in binary search trees. The right child of 3 is 4. So you can have a right child. This should not be here. That's a bug. The parent of 3 is 5. So you have something called the parent, which is just who are you the child of. And then we also call things descendants. So 2 is a descendant of 5 because it is somewhere in the tree below 5. Doesn't have to be the child, it can be the grandchild or the grand-grandchild, right? Each node has a pointer. We're going to assume that in our implementation of trees, each point is going to have a pointer to the left, the right, and its parent, okay? Sometimes you don't have a pointer to your parent, which makes some algorithms harder to implement, okay? In this case, in this class, we're going to assume that each node has a pointer to its parent. So you can actually go back up the tree, okay? Both children of 1 are null. So once you get to the leaves, they have nil. I will not draw these when we look at trees. And then the height of this tree is 3. The way we count the height is we count the number of edges to the bottommost leaf. Okay, so this hopefully should all be reviewed. Does anybody have questions on a tree? Cool. Okay, so what is a binary search tree? It's a tree that has it's a binary tree that has certain properties. So it's a subset of all possible binary trees. What a binary search tree says is that every left child or descendant, every left descendant is smaller than I am. Every right descendant is bigger than I am. Okay? Example, let's take these numbers and build it into a binary search tree. Okay, so there are binary trees, which just say I have 2 children, it can be any numbers. Now, a binary search tree is one that satisfies these additional properties, okay? Where the left is always smaller and the right is always bigger. So, for example, here we can take 5 to be our root. And then that means that we need to figure out everything that's smaller than 5 and everything that's bigger than 5, okay? You can imagine you could implement this, like let's say I give you a vector of numbers and you're trying to go from a vector to a binary tree, right? So we pick 5, maybe at random, and say this is my root. And then what do? Is I partition all my numbers to those that are smaller and everything that's bigger. And now I just have to make a tree out of these. So I can just call myself recursively, right? So I don't even have to worry about how I do this. When I actually implement it, I can just recursively call myself and be like, build me a tree with these values instead, right? So if you do that, maybe you pick 3 and then you call yourself recursively. You partition and call yourself recursively. And then that builds you a tree. Eventually you end up with something like this, okay? Is this the only tree that I could have built with these? No, right? Okay, that's a pretty easy question. This is not the only one. I picked 5 at random. It looks like a pretty good tree, I'll say. Okay. Any choice would have been fine. Hopefully, this reminds you a little bit of quicksort. Okay, taking an array and creating a binary search tree out of it is very similar to what we did with quicksort. It's almost the exact same algorithm, except you're making trees instead of sorting, right? So you can, so for example, what if I ask you, what is the best possible running time for making a binary tree out of an unsorted array? Yeah. Yeah. So it turns out that the best possible running time for a deterministic algorithm is n log n. Okay. That's the running time for quicksort in expectation as well. However, if you do implement it with quicksort, a lot of times it'll be faster than n log n because quicksort has some randomness to it. But in expectation, it's n log n. Okay. Cool. Intuitively, you can imagine like you're sorting the numbers, right? So fundamentally, if I could make a tree, a binary search tree, faster than n log n, then I could sort faster than n log n, right? Which we already know we can't do if we're using only comparison sorts. Okay. Right. So we're going back to definitions. Quick question. Are these binary search trees? Or which of these is a binary search tree? You guys think for a bit. Somebody that has not spoken up can answer. Yep. The left tree. So this one is a binary search tree. Cool. Why is that not a binary search tree?
Because index 1 is supposed to be under 2, basically, because it's smaller than 3. So it'll be under 2, also smaller than 2.
Perfect. Yeah. So if you look, so the tricky thing of this question was supposed to be, if you look locally at just this group, the left is smaller and the right is bigger. For every case, that is true. But the definition of binary search tree is that everything underneath you on the left side is smaller. And that is not true for 3, because you have a number that's smaller, but it's on the right side, on its descendants, right? So it is not enough to look at just the child, to figure this out. Cool. And this is not. All right. So like I mentioned, an aside, if you have a binary search tree, you can traverse it. It's called in-order traversal. We're actually going to learn about these different ways of traversing graphs. So actually a tree is a special case of a graph. So if you're comfortable with trees, you've already built up some intuition for graphs. In-order traversal, there's 3 different traversals, okay? And they're basically based on what order you call yourself recursively. So there's an in-order one, which says I call myself first on the left, then I do something, then I call myself on the right. There's another one that says I call myself on the left, then I call myself on the right, then I do something. And then there's another one where you do something, call yourself on the left, then call yourself on the right. Each of these actually give you different orderings, okay? For this specific one, we call it in-order traversal. We're going to do it. So what happens first is we start at the root, right? Then what we're going to do is we're going to call ourselves on the left. So we go to 3. Then we're going to call ourselves on the left again, right? Because when we call ourselves on the left, we still have not gotten to print 5 because we're calling ourselves on the left first every single time, right? So we go to 2, and then we call ourselves on the left of 2, which means we go to nil. And that's the base case, we do nothing, right? Then finally, we come back to 2, because now we're trying to get to this line. And that's where we print 2, okay? Then we're at 2, so we call ourselves on the right. Now that we finished the left, that does nothing. Then we come back to this function call on 2, but now we're done because we did the left and the right. So then we go back to 3, right? So here we're here where we called ourselves on 3, and then we did call myself on the left. Now we print 3. And then I call myself on the right. And then you can imagine the right also calls itself on the left first. It says it's null, I do nothing. Then it prints its value, calls itself on the right, says it's null, does nothing, right? So we print 4 only. Then we go back up to 3. 3 has already finished these 3 calls. It already did its left, and it printed itself, and it did its right. So it goes back up to 5. And now finally on 5, now we print 5, right? Because we finished all of the left, okay? Then we go to the right side of 5, and there we print 7. So how long does this algorithm take to run? What's the running time of this traversal? All of n, perfect. Why?
Because it's going through every single element in the tree.
Yep, that's one way to think about it. If our tree has n nodes, we see each node essentially once. So the running time is O of n. So again, what does this mean? If you keep thinking about it, it means that if I could take an unsorted array and make a binary search tree in linear time, then I can actually sort in linear time, because I would make a search tree in linear time, and then I would run this code, which is also linear, and then I'd get the array, right? Which is sorted. So you cannot make a tree faster than n log n for if you're doing comparison-based stuff, okay? Cool. So now it's sorted, runs in time O of n. Thank you. All right, so again, back to our goal. We're trying to walk through data structures that implement 3 things: search, insert, and delete. So how do we do these in a binary search tree? How do we do search? You guys want to give it a shot? How do we search for a particular key? Yeah, Leander? Got it. So he said compare the root, start at the root, see if that's the number you're looking for. If it is, you're done. You found it. If it's not, is the number you're looking for smaller or is it bigger? If it's smaller, you know it's not on the right side. So just call yourself on the left, right? So let's do it by example. So let's say I'm searching for 4. I guess I wanted to have more animations here, but you can imagine I search for 4 here, it's smaller. So when I go to the left, I search for 4 here. So I compare it to 3, it's bigger. So I go to the right, and then I compare it to 4, and I'm like, oh, I found you, right? How long does that take to run? Yeah, log n. Yep, that's perfect. It takes log n. Can we be a little bit more precise about how long it takes to run? So log n is close, but a binary search tree does not need to be balanced. So let's say I don't want you to use log, I don't want you to use n. How would you say the number of steps it took me, how does that relate to the structure of the tree? Yeah. It's equal to the height, okay? So just how tall the tree is, that's how long search takes, okay? The path of the longest height, okay? So there's a reason why we're saying it this way instead of log n, okay? Because it's actually not log n. So inserting into a binary search tree, I'm gonna skip a little quickly to some of these things, but basically what you would do is you would search for the value first. And then once you find it, you like insert it in the desired position. Okay, so there's a little hand waving. I'm not even going to ask you to implement this stuff, so it doesn't matter. This is mostly meant to be for review. But the pseudocode is you insert. So if you're trying to insert 4.5, first you find 4, and then you say, well, is 4.5 smaller or bigger? It's bigger, so I inserted it as the right child. Okay. There's another slide in the presentation that goes into more detail, but I'm just going to skip it. Delete, similar. I'm probably going to skip a lot of this, but essentially you search for the value first. If you find it, then you delete it, which ... there's like a little bit of extra work you want to do. Again, there's another slide in that I'm skipping that has the details, but some of this should mostly be review. Yeah, I'm going to skip these. So this is walking around, like if you're deleting, there's like multiple cases. You have to rewire the tree. So we're going to skip that, but you should be able to answer how long does delete and insert take. I will tell you that the operations you have to do to delete, like to actually delete a node once you found it, or to insert a new node is like constant time. You're not going to be walking the tree anymore. You're just going to move some pointers around. Yeah, Leander? Yeah, it's the same as search, because you always call search to find where you're going to insert or what you're going to delete. So it'll be the same running time as search, which is the height of the tree. So somebody did mention that trees have a height of log n. So somebody was like, well, the running time is big O of log n. We're done, right? Is that true? Not true. Is this a valid binary search tree? Yes. Okay. How long does it take to search in this tree? The height, which is O of n. Okay. Which is not log n. So it is not what we want. So what do we want? If we want search, insert, and delete to be log n, then we need the height of the tree to be log n. But the height might be big. So one idea is we can keep track of how deep the tree is getting. If it gets too tall, we can recreate a tree from scratch. That's one approach. It's fine, but that's one approach. Except every time you recreate the tree, you have to do O of n work. So one approach would be like, I just insert stuff into my tree, so it's a binary search tree. And then if I notice it's getting too tall, now I have all the numbers ahead of time. So I sort them, and then I create a new tree or something like that, right? But that is actually not very quick. Not a great idea. So instead, what we're going to review, I guess, is something called self-balancing binary search trees. There are many ways to do this. We're only going to cover one in this class, but there are many, many different. There's something called splay trees. There's something called AVL trees. And what we're going to cover is red-black trees. But there's many different ways to get the trees to balance themselves. Okay. Essentially, the idea for all of the different methods is that in order to maintain the binary search tree property, right? So that means that all of my left children are smaller and all of my right children are bigger, like all my descendants. What you can do is you can actually do what we call a tree rotation. Again, so these details are not super important. It should be some review from last time you took data structures, but it's mostly review. Hopefully, like it's not super important that we know the details. I'm probably not going to ask you to implement it. But yeah, so what you do is you can imagine like picking up this one. That gives you this weird tree that now has 3 children, which is like not valid, right? So I picked it up, and then the X fell down, and then it still has the A and the B as the children. Not binary. So what you can do is you can put the B here as the left child of X. Why? Why does that maintain the binary search property? Yeah. Yeah. So you know that B is bigger than Y. So it should be on the right child of Y. But you also know it's smaller than X because it's on the left side of Y. like it's on the left side of X. So that's why putting it on the left still makes it like it's still valid. It doesn't, right? It could be an entire tree, but you know that about this, right? So you can imagine picking it up, you get 3 children, and then one of these you can put on the left side of X, right? Still has the BSD property. Hopefully you guys can see that this takes constant time to do, because you're not having to change a lot of the tree, you're just moving pointers around, okay? And also remember that every node has a pointer to its parent. So if you need to go back up to the parent, it's like constant time as well, okay? So this seems helpful. For example, here, let's pick up the 5, let's rotate the 5, right? Then this is what it might look like. And it still maintains the binary search property, right? So this tree is like getting a little too tall, right? Like on the right side, it's like getting a little too deep here. So what we can do is we kind of like pick it up from the 5, and now it's more balanced, right? Just an example, intuitively. So our strategy might be, whenever the tree looks unbalanced, let's pick a node to rotate so that it gets more balanced, okay? So what you should be asking yourself is like, what do we mean by seems unbalanced? Like, how can you tell a tree seems unbalanced in constant time? Because if you're having to like walk through the tree again, like the entire tree, that's already linear, which is like too slow, right? And what do we mean by like okay? Like what's okay mean, right? So idea number 2 is we're going to follow that first idea, but it turns out that maintaining perfect balance, which means every single node except the leaves, except the level before the leaves, perfect balance is I always have 2 children, no matter what, except possibly for the leaves, which might be a little off, right? That's perfect balance. That's actually too hard to do. You don't need to know why, but it turns out it's like very hard to actually maintain perfect balance in constant time. So instead, what we do, and what all of the trees do, so AVL trees, splay trees, red-black trees, is they come up with a property of the trees that is a proxy for balance, okay? So if the tree satisfies this property, which is not every node has 2 children, it's some other slightly modified property that is actually weaker, it's a little weaker, then we say it's pretty balanced, okay? So, and then what we want is whatever this property is, which again, it is not every node has exactly 2 children. Can we maintain it with rotations? Like, can we maintain it as we insert new element in constant time? So if you ever want to design a self-balancing tree on your own, this is all you need. You need to figure out some property that you can maintain in constant time that keeps the tree pretty balanced. And ahead of time, keeping the tree perfectly balanced is too hard. So don't try that, okay? But if you do want to learn other data structures, again, like I mentioned, splay trees, AVL trees, they have different properties than what we're going to cover today. Today, we're going to cover red-black trees, but they all follow the same pattern, right? Yeah, so a red-black tree is a binary search tree that balances itself. This is supposed to be funny, but I guess I'm not that funny of a person. But anyway, no more time consuming. You don't have to hand balance it. Be the envy of your friends and neighbors with the time savings of red-black trees. Anyway, we're going to cover what they do exactly, but they balance themselves. So here is the proxy for balance that red-black trees use. Every node is going to be colored either red or black, okay? The root node is going to be a black node. There are modifications to this where you can have the root node be red. I think Wikipedia has it red. You can imagine it doesn't matter which color you pick as long as like there's 2 colors. The leaf nodes, so our nodes that have no children are going to be black, right? They have to be black. Children of red nodes are black nodes. So a red node cannot have a red child. It must have black children, okay? So every node is either red or black. The root node is black. The leaves are black, okay? And the children of red nodes are black. But the children of black nodes can be black or red, okay? So for all nodes X, the last thing is that all paths from X to the bottom of the tree have the same number of black nodes. Okay, so these properties are just defining what the tree looks like. This is the property that maintains the height. Okay, so it's saying that no matter for any x, for any node that I pick, if I count the number of black nodes to the bottom on any path that I can possibly take, it will be the same. So again, this is not the same as a perfectly balanced tree, but we will argue that it is very close. And it turns out that you can maintain these properties in constant time. So again, this is not something that you would necessarily ever come up with unless you're doing research into trees, right? Like there's a paper from the 70s, I think, that introduced these trees. And similarly for splay trees and like other trees, it's like probably years of people like trying to figure out different properties that will work. Okay, I'm not going to draw the null pointers at the bottom, but anyway, here's a few examples. So these are the properties that a valid red-black tree must obey. Okay, those are all 5 properties. So which of these are valid red-black trees? I did not draw the nil, so there's just assume the null ones are black. I didn't draw them. Yeah, so why don't you guys think a little bit through that? This will be on your homework, just FYI, like a similar example. Actually, on your homework, there'll be an example where I give you an empty tree and I ask you to color it so that it's valid. Jonathan, you wanna bottom right one? This one is, it is the red-black tree or it is not? It is. Who agrees or who disagrees with that? Huh? Bottom left, he says this one is the red-black tree as well. Who does no? Okay, Jonathan says this one's no. Why not? The root node is red. In our definition, it does, but you will see other definitions that essentially you can swap red and black in this definition and it works. But the key thing is that whatever is here needs to be like the root node. So if you say black here, if you're counting the black ones, that's the root. So it's like, yeah, I'm sorry. It doesn't matter, but it's like, it has to be consistent throughout the definition. Yeah. So this is not, yeah. Somebody says top left is red, black. Okay. So Jonathan said this one is red, black. Who agrees? Okay, you guys do agree. Okay, interesting. What about this one? Is this a valid? No, why not? Because the red node has a red child, and we say that all children of red nodes must be black. So these two are definitely not valid. Okay, so we're still looking at this one. Okay, so I will tell you, this one is a red-black tree. This is valid. This one is not. This one is not. For the last one, Leander, do you have? Yeah, what's up? The last one is not. Why? Got it. So remember, all paths from X to nil. So for every node, all paths must have the same number of black nodes. So from here to here, we have 1. From here to here, we have 2, right? So going from the root node to here, we have only 1. I guess here we have 2 black nodes. Going from here to here, we have 2 black nodes. But going from this node to the leaf, we have 1 black node. So it is not a valid red-black tree. Okay, so it violates this property. All paths from X, for all X, to the null pointers have to have the same number of black nodes. Okay. Why are these rules good? I guess we're probably going to cover this on Friday, I guess, but I'll wrap it up here, which is if you follow these rules, the tree is pretty balanced. Okay. Why? Because the black nodes are balanced. Okay. So essentially, we have a rule that says for every path, including the root, you must have the same number of black nodes. So if we ignore the red nodes, the black nodes are actually perfectly balanced. Okay. And then the red nodes are essentially spread out. So the reason the whole tree is not perfectly balanced is because you can have red nodes in weird places that prevent you from being a perfect balance. But what we're going to do is that they get spread out in a way that does not change the balance too much. So it should be clear to you that if I ignore the red nodes, the last property on the black nodes makes the tree perfectly balanced. So if I only look at the black nodes, it is perfectly balanced. But the red nodes can mess it up, but they don't mess it up too much. And that's why it's like a easier property than perfect balance, right? So we're essentially what happens is like half of the nodes are perfectly balanced, all the black ones. And then we allow about half of the nodes to be a little bit unbalanced, but we force them to be spread out across the tree. Because if you remember, one of the properties is that if you have a red node, you must have a black node as a child. Your child must be black. So we never have cases where we have just a long chain of reds, right? And that means that if all the blacks are perfectly balanced and we allow a few reds to be involved, but every red must have a black as a child, then the reds won't mess up the balance too much. Okay, so that's the idea. And then the key is we can actually maintain this property in constant time. So the rest of the slides cover how to maintain the property. It relies on rotations. It is a lot of cases and a lot of detail. You are not required to know for this class, but I think next lecture, we're going to finish up the proof as to why this tree is at most height 2 log n, okay? Which means it's O of log n. And then we're going to move to hash tables. All right, so that's on Friday. Hopefully, yeah, please come. We're going to cover hash tables and hash sets. That's a pretty important data structure to know. A lot of algorithms are so much faster if you can use hash tables with them. Okay, awesome. Thanks, guys. All right, everybody on Zoom, thank you. I will stop sharing.
All right, thank you.
All right, see you guys.